Introduction. Hey kids, today we will learn quantum mechanical model of atom. Matter has dual behavior wave as well as particle. Heisenberg's uncertainty principle is only applicable to small particle such as electron. The region of the atom where probability of finding electron is maximum is called orbital. Orbitals are characterized by a set of numbers known as quantum numbers. The energy, size, shape and orientation of the electron orbital can be specified by the use of three quantum numbers. There are principal quantum number, azimuthal quantum number and magnetic quantum number. So, throughout this model, we will quantum mechanical model of atom. Objectives. At the end of this lesson, you will be able to discuss dual behavior of matter, state Heisenberg's uncertainty principle, describe quantum mechanical model of atom. Towards quantum mechanical model of the atom, dual behavior of matter. In 1923, Louis de Broglie, the French physicist, proposed that like light, matter also has dual character. It exhibits wave as well as particle nature. He derived a relationship for the calculation of wavelength lambda and of the wave associated with the particle of mass m moving with velocity v as given by lambda is equal to h by mv or lambda is equal to h by p, where h is Planck's constant and p is momentum of the particle. The waves associated with material particles or objects in motion are called matter waves or de Broglie waves. According to the de Broglie concept, the electrons are not only particles but also have wave character associated with them. Therefore, for the wave to be completely in phase, the circumference of the orbit should be integral multiple of wavelength lambda. But from the de Broglie equation we know that lambda is equal to h upon mv. Hence, 2 pi r is equal to n into h by mv, where mvr is equal to n into h by 2 pi. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that it is not possible to determine simultaneously the position and momentum of a small moving particle, such as electron, with entire certainty. Mathematically, it may be expressed delta x into delta p greater than or equal to h by 4 pi, where delta x is equal to uncertainty in position, delta p is equal to uncertainty in momentum is equal to m delta v. Delta v is uncertainty in velocity of particle, m is the mass of the particle, h is equal to Planck's constant. So, it can be concluded that one can define the position of small particles. The less certainty one is able to define its velocity or momentum and vice versa. Significance of uncertainty principle. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for macroscopic objects. In case of microscopic objects such as electrons, the interaction of the striking photon of light with the particle will cause appreciable displacement of the particle from its normal path. As a result of this, the particle undergoes a considerable change in its path and velocity or momentum due to the impact of a single photon used to observe it. Thus, the very act of measuring the position of the microscopic particle causes a change in its momentum. The collision of photon with the electron sends it in an unpredictable direction. In our daily life, this principle has no significance. This is because we come across only large objects, that is, the objects which we can observe with naked eye, without altering their motion. The position and velocity of these objects can be determined accurately because in these cases, during the interaction between the object and the measuring device, the change in the position and velocity are negligible. Example: calculate the uncertainty in position of a dust particle with mass equal to 1 mg if the uncertainty in its velocity is 5.5 into 10 raised to the power minus 20 meter per second. Solution given delta V is equal to 5.5 into 10 raised to the power minus 20 meter per second. M is equal to 1 milligram is equal to 1 into 10 raised to the power minus 3 gram. H is equal to 6.626 into 10 raised to the power minus 34 joule second. From the formula, delta X into M delta V greater than or equal to H upon 4 pi. Uncertainty in position can be found as delta X greater than or equal to H upon 4 pi M delta V. Substitute the value of H delta V M, we get delta X greater than or equal to 6.626 into 10 raised to the power minus 34 divided by 4 into 3.14 into 10 raised to the power minus 3 into 5.5 into 10 raised to the power minus 20. Delta X greater than or equal to 9.59 into 10 raised to the power minus 13 meter. Reasons for the failure of the Bohr model. The wave character of the electron is not considered in Bohr model, and the orbit can be defined only if both the exact position and the exact velocity of the electron at the same time are known. This is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom ignores dual behavior of matter and also contradicts Heisenberg uncertainty principle. Quantum mechanical model of atom. Quantum mechanics is a theoretical science that takes into account the dual nature of matter, hydrogen atom and Schrödinger equation. Based on quantum mechanics, a new model of atom was developed, and this model is known as quantum mechanical model. In this model, behavior of the electron in an atom is described by an equation known as the Schrödinger wave equation, where x, y, and z are the three space coordinates. M is mass of the electron, h is the Planck's constant, E is the total energy, and V is the potential energy of the electron. Xi is amplitude of the electron wave and is called wave function. Sometimes the Schrödinger wave equation is written in the form h xi is equal to E xi, where h is a mathematical operator known as Hamiltonian operator. Significance of Xi. As a moving electron is associated with a wave, and a wave is completely defined by its amplitude. Therefore, Xi refers to the amplitude of the electron wave. It has got no physical significance. However, the square of Xi, that is Xi square, has a physical significance. In electron wave, Xi square gives the intensity of the electron at any point. In other words, the knowledge of Xi square is helpful in assessing the probability of electron in a particular region. Thus, Xi square is called probability density and Xi is referred to as probability amplitude. The solution of the Schrödinger equation for the hydrogen atom gives the energy levels that electron can occupy and the wave function of the electron associated with each energy level. Orbitals and quantum numbers. An orbital may be defined as that region of space around the nucleus where the probability of finding an electron is maximum. Orbitals are designated by a set of numbers known as quantum numbers. In order to specify energy, size, shape, and orientation of the electron orbital, 3 quantum numbers are required. These are principal quantum numbers, azimuthal quantum number, and magnetic quantum number. The principal quantum number, n. Principal quantum number tells us in which principal energy level the electron is present. It can have any whole number values such as 1, 2, 3, 4, etc. The energy levels or energy shells corresponding to these numbers are designated as K, L, M, N, etc. Energy of the electron in a hydrogen atom is related to principal quantum number by the following relation. En is equal to minus k square into 2 into pi square into m into e raised to the power 4 divided by n square into h square is equal to minus 2.18 into 10 raised to the power minus 18 divided by n square joule, where m is equal to mass of electron, e is equal to Charge on electron H is equal to Planck's constant. En is equal to energy of the electron in nth principal shell. N is equal to principal quantum number used to designate the principal shell. K is equal to Coulomb's law constant. Azimuthal quantum number L. Azimuthal quantum number determines angular momentum of the electron. This is denoted by L. The value of L gives the sublevel or subshell in which the electron is located. It also determines the shape of the orbital in which the electron is located. The number of subshells within a principal shell is determined by the value of n for that principal energy level. Thus, L may have all possible whole number values from 0 to n-1 for each principal energy level. For n is equal to 1, L can have only one value, that is 0. It means that an electron in first energy level can be present only in S subshell. L is equal to 0. So first energy level has only one subshell, that is 1s. For n is equal to 2, L can have values 0 and 1. It means that the electron in second principal energy level may be located either in S subshell L equal to 0 or P subshell L is equal to 1. So second energy level has only two subshells, that is 2s and 2p. For n is equal to 3, possible values of L are 0, 1 and 2. This implies that an electron in third principal energy level may be present either in S subshell L is equal to 0 or P subshell L is equal to 1 or D subshell L is equal to 2. So, third energy level has three subshells, that is 3s, 3p and 3d. Similarly, fourth energy level n is equal to 4 can have four subshells, 4s, 4p, 4d and 4s. Magnetic orbital quantum number ML.
Magnetic orbital quantum number refers to the different orientations of electron cloud in a particular subshell. These different orientations are called orbitals. The number of orbitals in a particular subshell within a principal energy level is given by the number of values allowed to ML, which in turn depends on the values of L. The possible value of ML range from plus L through 0 to minus L, thus making the total of 2L plus 1 values. Thus, in a subshell, the number of orbitals is equal to 2L plus 1. For L is equal to 0, ML can have only one value. ML is equal to 0. It means that S subshell has only one orbital. For L is equal to 1, ML can have three values, plus 1, 0 and minus 1. This implies that P subshell has three orbitals. For L equal to 3, ML can have 7 values, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. It means that F subshell has 7 orbitals.
Spin quantum number Ms. Spin quantum number determines the orientation of spin angular momentum. Spin angular momentum is quantized and can have two orientations relative to a chosen axis. This spin quantum number can have only two values, which are plus half and minus half. The plus half value indicates clockwise spin represented by an arrow pointing upwards, and the other indicates anti-clockwise spin represented by an arrow pointing down. Shapes of atomic orbitals. An orbital wave function psi can be written as a product of two functions, the radial function and the angular function. So, the complete wave function represents an orbital in which the radial part psi r depends upon quantum number n and l, and it tells us about the size of the orbital, whereas the angular part depends upon quantum number L and ml and tells us about the shape of the orbital. The positive and negative signs indicate that the orbital wave function is positive or negative in a particular region. It has been observed that s orbitals are independent of angular wave function. All s orbitals are spherically symmetrical. P and d orbitals depend upon radial as well as angular wave function. Shapes of atomic orbitals. Probability density. A graph of psi square as a function of distance from the nucleus is called probability density curve. The regions of space around the nucleus where the probability of finding the electron is maximum are called orbital. Boundary surface diagrams. A boundary surface, also known as contour surface, is drawn in space for an orbital on which the value of probability density psi square is constant. A boundary surface which encloses the regions of maximum probability, say 90%, best describes the shape of the orbital. The boundary surface diagrams for s orbitals are spherical in shape. The size of the s orbital, however, increases with increase in value of n. The boundary surface diagrams of 3 2p orbitals are not spherical. Each p orbital consists of 2 lobes which are separated by a region of zero probability called node. The 3 2p orbitals lie along x, y and z axes respectively and are designated as 2px, 2py and 2pz. Charge cloud picture of orbitals. For s orbitals, the probability of finding the electron is same in all directions at a particular distance. In other words, s orbitals are spherically symmetrical. The s orbitals of higher energy levels are also spherically symmetrical, however, they are more diffused and have spherical shells within them where probability of finding the electron is zero. These are called spherical nodes. In 2s orbitals, there is one spherical node. Energies of orbitals. A diagram representing relative energies of various orbitals in an atom is called energy level diagram. In hydrogen atom, there is only one electron which is present in orbital in ground state. However, in excited state, the electron may jump to any of the orbitals belonging to higher energy levels. All the orbitals of a particular energy level have same energy in hydrogen and hydrogen-like atoms. For example, 2s and 2p orbitals have same energy. The orbitals having the same energy are called degenerate orbitals. Energy level diagram of multi-electron atoms. In case of multi-electron atoms, the energies of various orbitals depend not only upon the nuclear charge but also upon the other electrons present in the atom. Main characteristics of this diagram are: number 1, the different subshells of a particular energy level may have different energies. For example, energy of 2s subshell is different from the energy of 2p subshell. Number 2, in a particular energy level, the subshell having higher value of L has higher energy. Increasing order of energies of different types of subshells in a particular energy level is: number 3, as the value of N increases, some subshells of lower energy level may have energy higher than the energy of some subshells of higher energy level. Number 4, the increasing order of energies of various subshells is: the relative order of energies of various subshells in a multi-electron atom can be predicted with the help of N plus L rule. According to this rule, number 1, in neutral atoms, a subshell with lower value N plus L has lower energy. Number 2, if two subshells have equal value of N plus L, the subshell with lower value of N has lower energy. Filling of orbitals in atoms. Aufbau rule. According to this rule, the electrons are added progressively to the various orbitals in their order of increasing energies, starting with the orbital of lowest energy. Increasing order of energies of various orbitals are: Pauli's exclusion principle. This principle states that no two electrons in an atom can have same set of all the 4 quantum numbers. From this, it follows that an orbital cannot have more than 2 electrons. Moreover, if an orbital has 2 electrons, then they must have opposite spins. Hund's rule of maximum multiplicity. This rule states that the pairing of electron in the orbital of particular subshells p, d or f does not take place until all the orbitals of the subshell are singly occupied. Moreover, the singly occupied orbitals must have the electrons with parallel spin. Electronic configuration of atoms. In order to represent electron population of an orbital, the principal quantum number n is written before the orbital symbol, while the number of electrons in the orbital is written superscript near the right-hand top of the orbital symbol. If we have 2 electrons in the s orbital of first energy level, then it is written as 1s squared. For hydrogen, for helium, for lithium, for beryllium, for boron, for carbon, for nitrogen, for oxygen. Stability of completely filled and half-filled subshells. The completely filled and completely half-filled subshells are stable due to symmetrical arrangement. The electronic configuration in which all the orbitals of same subshell are either completely filled or exactly half-filled have relatively more symmetrical distribution of electrons and therefore lend more stability to the system. Stability due to exchange energy. The half-filled or fully filled degenerate orbitals have more number of exchanges and consequently have large exchange energy of stabilization. The exchange means shifting of electrons from one orbital to another within same subshell. Let us compare the number of exchanges in 3d4, 4s2 and 3d5, 4s1 configuration of chromium. Thus, in 3d4 arrangement, electron exchanges are 6, which implies that there are 6 possible arrangements with parallel spin in 3d4 configuration. The total number of electron exchanges in 3d5 arrangement is larger, which lends it to greater stability. Did you know? Atom scale imaging unlocks exact structure of glass. Intel plans to release its first 22 nanometer quad-core atom system on a chip at the start of 2014. Summary. Let us summarize what we have learned. Matter exhibits wave as well as particle nature. Wavelength of the wave associated with a particle of a mass m moving with velocity v as given below, where h is Planck's constant and p is momentum of the particle. Heisenberg's uncertainty principle states that it is not possible to determine simultaneously the position and momentum of a small moving particle, such as electron, with entire certainty. Mathematically, it may be expressed as Schrödinger wave equation, where x, y and z are 3 space coordinates. M is mass of electron, h is Planck's constant, E is the total energy and V is the potential energy of the electron. Xi is amplitude of the electron wave and is called wave function. Principal quantum number tells us in which principal energy level the electron is present. It is denoted by n. Azimuthal quantum number determines angular momentum of the electron. This is denoted by L.
Magnetic orbital quantum number refers to the different orientations of electron cloud in a particular subshell.
This is denoted by ML. According to Aufbau rule, the electrons are added progressively to the various orbitals in their order of increasing energies, starting with the orbital of lowest energy. Pauli's exclusion principle states that no 2 electrons in an atom can have same set of all the 4 quantum numbers. From this, it follows that an orbital cannot have more than 2 electrons. The completely filled and completely half-filled subshells are stable due to symmetrical arrangement and stability due to exchange energy.